Okay, it's 1 o'clock, so let's go ahead and get started. All right, so good afternoon, everybody. How's everyone doing on this fine Thursday afternoon? Hopefully, we won't have too many Clippers fans in the class. I think, you'd probably be pretty sad at this point, given what happened on Tuesday night. But, I myself, I'm a Lakers fan, so I enjoyed it quite a lot. Although, of course, I'll be happy if the Lakers win the championship. So the plan for today is we're going to continue on with our lecture notes on present worth analysis. So we basically went over the basics of present worth analysis last week. Actually, forgot Tuesday we had James come here, and so today we're going to go over what happens if you have some situations that don't match up pretty well. Okay. Before we get started, are there just any questions about the class, or I know there's a homework out there for you guys right now. Any questions on that I can answer before we get started? Okay, so let's go ahead and get rolling. Okay, so just like I just mentioned, we went over just the basics of present worth analysis before, which is, the idea is that we want to, the reason we use present worth analysis is so that we can compute basically a single number to basically sum up the economic efficiency of different options. And then using that present worth value, we can choose between different options to see which one makes the most sense, at least from an economic point of view, right? So all the examples that we've done so far, all of them had the same project life, or they all lasted for the same years. And one of the first things that we said when we began this unit was that if you're comparing two different alternatives, they need to have the same project life. Otherwise, it's not really fair to compare different things. Okay? But a lot of times, when you're working out in the real world and you're comparing like two different vendors, they're oftentimes going to have different project lives just because they make different products, right? And so the first thing we're going to do is how do we do comparisons when our alternatives have different project lives? Okay. Okay. And so I think probably the easiest way to do the first method is to just come up with an example, right? And so let's say that we have a situation where we're comparing product A, okay, where product A has its initial cost, maintenance, salvage value, all that good stuff, but it has a useful life of 4 years. And so we're deciding if we want to go with product A or with product B. Okay. So product B is a comparable product. It's one of the competitors, and so it has its own initial cost, maintenance, and all that. And so it does roughly the same things as product A, but instead of lasting 4 years, let's say that this one lasts 8 years. And so we want to be able to compare these two and see, which product makes the most economic sense to purchase, right? And so we can't just straight up just apply our present worth analysis to this because they have different product lives, right? And so just by, like say you're using the equations to compute these guys, you're going to plug in different values of n, and you're going to get very different answers that it's very hard to compare the two. Okay, so we cannot apply present worth straight up. Okay. And so in these particular cases where your two products or two alternatives have different lives, one thing that you can do is you can just simply compute the least common multiple between them. Okay? And so the first method kind of in dealing with comparisons with different project lives is the least common multiple. And so the way that you do this is very simple. And so you look at the product lives for each of the different alternatives, and you compute their least common multiple, right? And so in this case, the least common multiple is 8, right? And so project B lasts for 8 years, and if we take 2 times product A, then we also get 8 years as well. Okay? Right? But then, the question is, if we extend our analysis to 8 years, what do we do with product A? Okay. Okay. So for the cases where the product life is less than the least common multiple, in these cases, what we do is we simply just once product A has lived its life for 4 years, what we assume is that in year 4 we just simply buy a replacement. So we just buy a new. Okay. 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 And when we do buy a new one, we're going to assume that it's going to be the same price, which is a really big assumption. So anyone who's tried to buy a 5-year-old computer part 5 years later knows that it's never going to be the same price. But just for the simplicity for our analysis, we're going to assume that the replacement that we buy 4 years later is going to be the same price. Okay. All right. Any questions on this before we do an example? Okay. Okay. So let's do a real example with numbers. Okay. All right. So let's say that you're working for Southern California Edison, right? And they're considering the purchase of a new pump. Okay. So we can say that SCE, Southern California Edison, considering purchasing a new pump. Okay. And so let's compare the options. So let's say we have pump A. Okay. So pump A has an initial cost of $7,000. Okay. It has an annual maintenance cost of $1,500. Okay. And a salvage value of $1,200 after 12 years. Okay. And so right off the bat, we can see that the product life for pump A is 12 years. Okay. So that's pump A. Now let's look at pump B. Okay. So pump B offers a pump at $5,000 initial cost. Okay. The maintenance cost is $1,000 each year. Okay. And $1,000 salvage value. Okay. But pump B is only going to last 6 years. Okay. All right. And so if we assume an interest rate of 7%, okay, what we want to do is we want to choose the pump that's the most economically efficient. Okay. And we're going to assume in terms of performance and everything, both these pumps perform the same as the other. Okay. All right. And so you can see right away, we have a problem, because normally when we do present worth, we use product lives that are the same, but in this case, our product lives are different. Okay. And so one of them is going to last 12 years and the other one's going to last 6. Okay. And so remember, for these cases where the product lives are different, we just use the least common multiple, and our least common multiple here is going to be 12 years. Okay. And so what that means is that when we do the present worth analysis for pump B, we're going to buy a new pump at 6 years at the exact same price. Okay. All right, so for this particular problem, what I'm going to do is I'm going to draw the cash flow diagrams for both of these pumps, just so you kind of just so you can kind of see what they're like, and then we'll perform present worth analysis on. Okay. All right. Any questions on the problem setup? Okay. Okay. So let's draw the cash flow diagram for pump A. Imagine these are all spaced evenly. Okay. And so pump A, we had an initial cost of $7,000. So let's go ahead and draw that guy in. We have a yearly maintenance cost of $1,500. So every year we're going to have $1,500. Let me use a different color just to illustrate that. Okay, so all these guys are going to be 1,500. Okay. And then at the end of 12 years, we have a salvage value of 1,200. Okay. So this is going to be 1,200. Okay. So fairly straightforward. So it's a very, typical, you buy a device, you maintain it for, in this case, 12 years, and then you sell the parts at the end. Okay. All right. So now let's compare that to pump B. Right, so we have our 12-year horizon. And so pump B, we have an initial cost of 5,000. Okay.
Professor.
Yep. Mm-hmm.
For pump B, we have a salvage after 6 years. So
Yes.
why you have 12?
Remember, so because we're doing a present worth analysis, we have to extend our time frame so that we can compare them on the same time frame. So because pump B has a shorter time frame, what we're going to do is that at year 6 we're going to buy a replacement, just like we kind of talked about before. So I'll show you what that looks like from the cash flow diagram. Right?
Okay.
Okay. And so just like was mentioned, we have a yearly maintenance of 1,000. And then we also have our salvage value here. So our salvage value here is also 1,000. Okay. But that's only for the first 6 years, right? And so we won't be able to actually compare this with pump A because, we can't compare something that only lasts 6 years to something that lasts 12. And so what we're going to do at year 6 is we're just going to buy a new pump that's exactly the same as before at the exact same price. Okay. And so also on year 6, we're going to have an arrow down. And we're going to basically repeat our initial cost. So our initial cost is 5,000. So we're going to buy a new one at year 6. Okay. Just pretend that those two arrows are the same. Right? And then from years 6 to 12, we have our maintenance cost. So all these are also $1,000. Okay. And then we have our salvage value at the end of 1,000. Okay. And so, now that we have these two cash flow diagrams and they all last the same years, we can actually compute the present worths, and then they're going to, we can compare apples to apples. Okay. Okay. Any questions on this?
Would you add the 1,000 and the 5,000 on year 6?
Yeah, you can do that. I'm keeping them separate just because one thing that we can do is we can say we just have a uniform series of 1,000 that goes from 0 to 12. And then we can compute the $5,000 cost separately from that as just one future sum. So, but if you want to put it as 6,000 on there, definitely go ahead. But I think the computation is a little bit easier if you keep it separated as just one uniform series all throughout.
Gotcha. All right.
Yeah. Okay. So let's compute the present worths, right? And so let's start with the present worth of A. And so remember, with present worth analysis, we're going to take all the cash flows in our problem and compute them to a present sum, one single lump sum in the present day. Right? And so for pump A, what we have is an initial cost of $7,000. Okay. And so the nice thing about that is that, you know, $7,000 is something that we pay today, so we don't have to perform any conversions. Okay. Next, we have our yearly maintenance costs. So our yearly maintenance costs are a minus 1,500. Okay. And that 1,500 is a uniform series, which is an A. And so we need to convert this to a P. And so if we want to use the compound interest table, we would go into the P over A column, and then we're going to use an interest rate of 7%. And then we're going to do it for 12 years. Okay. Okay. And then in addition to that, we also have our salvage value. So our salvage value is going to be a positive because we're going to make money off that. A positive 1,200. Okay. And that 1,200 is a single sum in the future. So in order to convert that to a present day, we need to do a P over F. Right? And so in our compound interest table, we go to the P over F column, and then we use 7%, and then 12. Okay. Okay. And so you can look up these values in the compound interest table. It's a little bit easy, you know, these are once, you know, you're starting to see that once you start to get to these kind of longer problems, the compound interest table makes it a little bit easier. Okay. And so if you look this value up in the compound interest table, you'll see that this is 7.943. And then this value P over F, this is 0.444. Okay. And so if you do that, what we get is the present worth of A is equal to minus $18,381.70. Okay. And so that's our single number. So, you know, basically paying for this pump and maintaining it, and after selling it, it's the same thing as if we just forked over $18,381.70 today. Okay. And so that's the economic value for pump A. And so let's compute the economic value for pump B. And so pump B, we have our initial cost, which is $5,000. Okay. And that's happening today. Okay. And then since we have to buy a replacement, we have to factor that into here. Okay. So we have to subtract another 5,000. But since this replacement occurs in year 6, we have to convert this to our present day, right? And so that single cost in year 6 is going to be its future value. And so to convert it to a present sum, we have to multiply it by the P over F factor at 7%, and then at 6 years, because you know, this replacement happens at year 6. Okay. Next, we have our yearly maintenance costs. We can have a subtract of $1,000. Okay. And this happens for all 12 years, so it's going to be 12. Okay. And then we need to add our two salvage values. Okay. And so we're going to add $1,000. Okay. And the first time we sell the parts for the pump are going to be in year 6. So we're going to do a P over F, 7%, and 6. Okay. And then to this, we're going to add another 1,000. Okay. And that's going to be P over F, again, 7%, and then 12. Okay. Because our last sale happens in year 12. Okay. Okay. And so if we you know, look up all these values in the compound interest table, what you get is what you get is 15,000 minus 15,164.20. Okay. And so based off these solutions, what do you think is the more cost-efficient pump for Southern California Edison to buy?
Pump B.
Pump B, that's correct. Yep. Which is not intuitive at first, right? So you think like you buy pump B and you say, you know, yeah, it costs less, but we have to buy a new one after 6 years. But, you know, because of the interest rates and the way everything works, you actually save yourselves over $3,000 in present day money by going with pump B. So even though it might seem like it's a hassle to buy a new pump, after 6 years, it's actually more economically efficient. Okay. And I think this is a nice example because it's something that you might not have seen kind of just by looking at the numbers initially from the problem. But the combination of the interest rates and, you know, in this case, the maintenance cost was a lot less too. we were able to see that pump B was a much more efficient option. Okay. And so, I'll say one more thing too, that, or just to emphasize that this assumption where we basically buy a replacement 6 years in the future at the exact same cost, like this is a huge assumption. So most of the time in reality, this is not going to be the case. But for the problems that we're doing, that's it's going to be okay, just because it kind of helps just with the numbers. Okay, are there any questions on this example here?
Yeah, Professor.
Yep.
So for the second, for PWB, and then for the second conversion from future sum to present sum.
Yep.
Why is it 12 and not 6?
Which one? Which one are you talking about? The 5,000?
No, the 1,000 times P F to P, 7%, and then 12.
So we sold it twice. And so remember, we sell our first pump at year 6, and so that's the first one. And then the second pump that we buy, we sell it again in year 12. And so we have one sale at year 6, one sale at year 12.
Oh, okay.
Yep. All right. Any more questions on this? Okay, so that's the least common multiple technique. And so if your numbers are convenient like that, then that works well. Okay. But what happens if you have two products where their product lives are very different from each other and the least common multiple is really high? Okay. And so let's say that we're comparing two products. Okay. So let's say that product A lasts for 7 years. Okay. And then we have product B. Product B lasts for 13 years. Okay. And so if we compute the least common multiple of this, and we have these beautiful prime numbers, what we get is 91 years. Okay, so the least common multiple, LCM, is 91 years. Okay.
Is this another example?
So it's just a hypothetical right now, and then we'll actually do an example with numbers in just a second.
Gotcha.
Yeah. So you can see in this case, least common multiple is 91 years. So that's longer than maybe some of us will be alive on this earth. So this is not kind of a, even though it's the least common multiple between these two guys, you're probably not going to be using a product for 91 years such that your analysis is useful. And so when your least common multiple is something that's like really big like this, where it's kind of like unreasonable that you would use it for this long, then you're going to have to use something else. Okay. And so in these situations where the least common multiple is really unreasonable, one thing that you can do is you can assume that you're going to salvage Earth. Okay. Okay. And so what I mean by early salvaging is that you're going to sell the parts, or you're going to sell your machine before the life of the machine is up. Okay. And because of this, like you'll have to estimate, because because you haven't used the machine for the full length, you can sell the machine often for higher than what you would have if you use it for the whole time, right? And so usually for these kinds of problems, I'm going to give you the early salvage value, because it's very domain specific. Where if you just ask kind of a random person, like say if this industrial pump is designed to use for 8 years, but you only use it for 5, how much do you sell it for, right? So that's very domain specific, where you would have to be a huge expert on pumps and maybe study it for like the rest of your whole life to really know what that number is. So for these kind of particular problems, I'll give you the early salvage value, so you don't have to worry. That's something I'll give you, but you just have to know how to use it. Okay. Okay. So let's do an example showing this. Okay. And so we're actually going to use these two lives. Okay. But in this example, let's say we have a diesel manufacturer, and it's considering two different production machines. Okay. Okay. And so we have two options. We have option A, and we have option B. Okay. Right. And so each of these guys will have an initial cost. Okay. So they'll also have a salvage. And the important thing with this salvage is that this is the end of life salvage. So if you use it for the entire lives, this is what they're going to be. Okay. And then down here is the useful life. So for how long you can use these products. Okay, so option A has an initial cost of $50,000, or 50,000. And option B has an initial cost of 75,000. Okay. And so the end of life salvage value for option A is 10,000. And the end of life salvage value for option B is 12,000. Okay. And then just like up there, let's say that option A has a useful life of 7 years. And then option B has a useful life of 13. Okay. Okay. And so what you want to do is you want to use present worth analysis in order to find out, which machine is best. But you can't find a least common multiple here because, you're not going to be using the same machine for 91 years. Okay. Okay. And so to basically help you out with this analysis, you contact the manufacturer, you contact the vendors that are giving you these guys, and then you're going to say, I only anticipate us using these machines for 10 years. So can you give me an early salvage value, right? Okay. And so the vendors get back to you and they say, okay, if you sell these machines at this date, this is what we kind of estimate what you can sell. Okay. And so the option A says that if you use our machine for 3 years, and you sell it after using 3 years, you'll get a salvage value of $20,000. Okay. And option B says that okay, if you use our machine for 10 years, you'll get a salvage of 15,000. Okay. And so those are the early salvage values that are given to you. Okay. And so from this analysis, or from these numbers, what we can say is that we can perform a present worth analysis with a horizon of 10 years. Okay? And so basically what we're going to do is that, for 10 years, we're basically going to use option A. We're going to use our first machine for the first 7 years because that's the product life. And then at year 7, we're going to buy a new machine A, but then we're only going to use it for 3 years and then sell it at 3 years. Okay? And then we're going to sell the second machine for 20,000. Okay? And so for option B, we only have, we're not going to use it even for its full first life. And so we're going to use it for 10 years and then salvage it for $15,000. Okay? All right, any questions on just the problem setup? Oh, we need an interest rate. We need an interest rate. Interest rate is 8%. All right, any questions on the problem setup and how we're going to go about doing this? Okay. So let's go ahead and get started. So let's start with the cash flow diagrams. And so cash flow diagrams, you might think they're kind of annoying just because they take up a lot of space, but sometimes they're really useful, especially when you have a lot going on. So let's draw the cash flow diagram for option A. Okay. And so we're going to have a cash flow diagram for 10 years. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Okay. Okay, so first thing is we have our initial cost. So our initial cost is going to be $50,000. Okay, right? And so product A has a useful life of 7 years. So at year 7, we're going to sell it, and we're going to sell it for its end-of-life salvage value. And so from the table on the first page, we know that our end-of-life salvage value is 10,000. Okay. Right, but we're not done yet. And so since we want to use these machines for 10 years, after our first machine breaks down in year 7, we're going to buy a new machine for another $50,000. Okay. Okay, so we buy our new machine at year 7, and then we're only going to use it for 3 years. Because remember, we only have we've set the early deadline to be 10. Right? And so in year 10, we're going to sell it for its early salvage value. And its early salvage value is $20,000. Okay. Okay, so that's option A. So now let's do option B. Okay. And so option B, we have our initial cost. And so our initial cost is, in this case, why does it keep doing that? Okay.
Professor,
Yep.
can you tell again how you get the 20 salvage value for A?
Yeah. So that's always going to be given to you. So just like I was saying before, that like the 20,000 or the early salvage values, those are very domain specific. And so I would have to tell you explicitly in the problem what those values are going to be. So that's basically what I said down here, is that these early salvage values are given to you here in the problem.
Okay, my bad, yeah.
Okay, and so for option B, this is actually pretty easy. And so option B, we just have an initial cost of 75,000. Okay, oh, that's why. Okay, and then at year 10, which is even before we even use up the first one, we're going to sell it for an early salvage value of $15,000. Okay. Okay. And so from these guys, you should be able to compute the present worth from these two cash flow diagrams, where they're both at the same length, but they have different cash flows. Okay. All right. Any questions on the cash flow diagrams? Okay. So let's compute their present worths. Okay. So let's do present worth of option A. Okay. So in option A, we have first our initial cost. So initially at year 0, we buy it for $50,000. Okay. Right. And so since this machine A is not going to last for the full 10 years, we're going to have to buy another one at year 7. Okay. And so our purchase at year 7 is a single sum in the future. Okay. And so in order to convert that to a present value, we do multiply by a P over F factor at our interest rate 8%, and then at 7 years. Okay. Next, we have to add our salvage value. So our salvage value at 10,000, that's our end of life salvage value, and that's going to occur in year 7. Right. So again, this is a single sum. So it's a P over F, 8% and 7. Okay. And then we have to add in our salvage value at year 10, which is a $20,000. Right. So we have $20,000, P over F, 8%, and then this is at 10 years. Okay. And so we add those up, we look up these numbers from the table, and then what you get is minus $64,000 and 76, or $64,076. Okay.
For this example, could we have done minus 40,000 because the 10 and the $50,000 occur at the same time? Would that occur the same answer?
Yeah. In this case, you could definitely do that because they occur at the same time. You can just simply add them together.
Thank you.
Yeah, so that's actually a good point to bring up in general, whereas like if you're looking at your cash flow diagrams and you see two things happening at the same, or two cash flows happening at the same time, and so because they're happening at the same time, you can just simply add them together because, you know, there's no time that's going to pass where the interest rates are going to take effect. And so for these cases, you can just simplify that and just do a minus 40,000. Yeah. Okay. And so let's do the present worth for option B. Okay. So in option B is a little bit simpler. So we just have our initial cost. So our initial cost is minus $75,000, dollar sign. Okay. And then to this, we're going to add our early salvage value in year 10. Okay. So we're going to add 15,000. Okay. And that's P over F, 8%, and then 10 years. Okay. And so you add these together, and what you get is minus $68,000. $68,000 and $68,052. Okay. And so what you see here is that option A is the better one, even though it only lasts for a certain amount of time. Okay. And so, you know, both these examples that we've done today kind of illustrate kind of the same point where, you know, you would think that, you know, buying a replacement or buying a cheaper one and then having to replace it several years later, that's going to be, you know, inefficient. But, you know, what you get by doing this is that, you know, today you only have to pay $50,000 versus $75,000. And so you have basically $25,000 today to use for other stuff. And remember what we always say is that money has more value to you now because you can always use it to invest in other stuff or, you know, do other stuff with it. Right? All right, so the question is, why was n equal 10 again for the early salvage value? So that's something arbitrarily set by the problem. So usually the way that you set that in practice is that, you know, you say that you only plan on using these machines for X amount of years. So like if you think about your car, right? So you think like, I'm only going to use this car for 10 years, and then that's how you basically set it. So in cases where there's not a convenient least common multiple, you have to kind of ask yourself, you know, how many years do I plan to use this machine or use this device? But for, you know, for the purpose of this class, most of the time I'll just give you that value just because I also need to give you the early salvage values as well. Yep. All right. Any more questions on this example?
Yeah, Professor. Is it always going to be this way where like if you buy a replacement, it's always going to be better than like the other example, like just buying a more expensive one?
Yeah, that's a great question. So for these two examples, you know, buying the option with the smaller product lives was better, but that's not necessarily always going to be the case. So if we change these numbers up, where instead of $50,000, we have an initial cost for A. Let me see. So we say the A initial cost was something like 70,000, right? And so we have 70,000. You know, that's going to change our numbers up quite a bit. And then this is it's not going to be like this. So in that case, it'd be better to buy option B. So you know, it really depends on the numbers, and you kind of have to run them through. But that's usually if there's a big difference in initial cost like this, like here it's like a 50%. You pay 50% more for option B versus A, then probably the cheaper one is going to be better.
Oh, okay, so it depends on the initial cost.
Yeah, the initial cost is a big indicator because that's something you pay today, right? And remember, the costs that you incur today, those are always going to be the most significant for these guys.
All right. Thank you.
Yep. Okay. So those are two different methods that you can do for performing present worth when the product lives are different. And so let's kind of go over a specialized case where a lot of times when you think of like buying an engineering purchase, you think that you're not going to use it forever because machines break down and stuff like that. But there are some engineering products where like it actually does plan to last until the end of time, right? So you think of like a lot of public works projects or a lot of government projects, like you work on the road, right? I hope that we're still going to be using the same roads, for the whole future. I mean, granted, you have to maintain it for a while, but the initial cost of the government putting down the road, that's just going to be kind of a one-time cost. Okay, and so what do we do in those cases, or how do we compute present worth? or how do we use what we know for products with an infinite analysis period? Okay. And the kind of and the concept behind this is something called capitalized cost, and I'll define that in a second. Okay. And so the situations where you would have an infinite analysis period, most commonly these would be like public works projects, right? So you're talking like your sewers, your bridges, your canal systems, your drainage, all the infrastructure that that the government usually puts down. Right? We hope that these things last forever. Now, proper maintenance is a different story, but we can talk about that another day. So in the case where you expect to be maintaining and doing something for eternity, right? So in these cases, your n, for all intents and purposes, will be infinity, right? And so you can go to your compound interest tables and you can try to find n is equal to infinity, but you're not going to find it, right? And then even if you're using the formula, so if you try to plug in n is equal to infinity into any of the formulas, you're just going to get infinity again, right? And so what do we do in these cases, right? Or how do we even begin to analyze cases where the n is equal to infinity, right? Okay, so we have another definition, right? And so let's define capitalized cost. And so capitalized cost is the amount of money that you would need to set aside now okay? And if you're given some interest rate, okay? And so it's the amount of cash that you would set aside now, and if you invest that at some interest rate, that would yield you basically a uniform cash flow indefinitely. Okay. And so basically the way that you can think of this is that, say you take, a certain amount of money, you stuff it into a bank account with a certain amount of interest rate, and then each year or each month on that bank account, you're going to be making some money on the interest. And then what we're saying is that at the end of each month or at the end of each year, you take that interest payment and you withdraw that every single month. So basically by investing that large amount of money at first, you basically kind of get passive income just from the fact that, you're earning it based off the interest. Okay, and so the way that we compute this is that, say that we have some present amount of money, P, and so P, is the money that you have today, right? And then you invest it at some bank account or in some project with a known interest rate, right? And so after 1 year, your money is going to grow by this amount. So your money is going to grow by the interest rate multiplied by your initial investment. And so this right here, this is the interest that you gained from this year, or this period, I should say. Okay. And so, you know, say you have this bank account, the only thing you're going to withdraw is just this amount. So just whatever interest was on top of your initial investment, that's all you're going to withdraw. Where your initial investment, P right here, this right here is your capitalized cost. Okay. Okay. And so the important thing about capitalized costs is that your initial investment, you basically just don't touch it. And so you leave basically at least the same amount in your account all the time. And so that every year you can just collect on the interest rate. So you leave it, you just leave that initial investment right there. And so say that, you know, every year you want to make a certain amount of money just based off the interest, the capitalized cost is how much money you have to put in initially in order to make that. And so I'll do a couple examples to kind of make this more clear, because it's a little bit of a strange concept. All right, any questions on this? Okay. Okay. And so let's do just a very simple example that that you can do with your finances, if you can find a bank that will pay you 8% interest, which is very difficult nowadays. And so say that you have $1,000. Okay. And let's say that you found the bank of very nice people, and this bank is saying, if you deposit that $1,000 for us, we'll give you an 8% interest rate. And so we can just simply compute, you know, how much money that you're going to make. You know, let's say that this is per month. So every month they're going to pay you 8%. Okay.
Professor, it's interest on what? This is like a 1,000?
Yeah, interest on 1,000. Okay. Okay, so each month the bank is going to pay 0.08. Oops. Multiplied by 1,000. Okay. So each month the bank is going to pay you basically 80 bucks. Okay. Okay. And so if you take that 80 bucks and you withdraw that every month, so if you withdraw basically the interest basically as soon as you make it and you deposit it into your checking account, then you know, this is basically the same thing. It's the same thing as having basically a uniform cash flow of $80 per month. Right? And so basically the way that you're earning this $80 per month is just by the fact that you deposited a large amount of money at first. Okay. And so you know, and so in order to produce this $80 of passive income, what you had to pay up front was $1,000, right? And so in this particular case, in order to earn your $80 per month, just from this bank account, you had to pay a capitalized cost of $1,000. Okay. Of $1,000, sorry. Okay. And so we can come up with a formula for capitalized costs. And so say that we, in this case, we wanted to have a monthly or a uniform series of $80. Okay. And so that's going to be our A. Okay. And so the capitalized cost is simply just going to be A divided by I. Okay. And so you just take basically the amount of money that you want to earn each period, and then you just divide it by the interest rate, and that's going to be your capitalized cost. Okay. All right. Does this example make sense to everybody? Okay. Okay. All right. So let's do a little bit more of a realistic example that you might see, if you work for like the government or Caltrans or something like that. Okay. And so let's say that, City of LA, they want to build a new pipeline for water. Okay. Okay. Right. They have to build a new pipeline to carry all the Clippers fans' tears, right? And so, this is something, because Clippers are probably going to suck for the rest of eternity. This is going to be a pipeline that's going to be used for, the rest of, eternity. Okay. And so, basically, what the city wants to do is it wants to basically set aside the money now so it can maintain this pipeline forever. Okay. Okay. So let's put some numbers on this. So this pipeline will cost $8 million. And so this will be our initial cost. Right. And so basically, in order to maintain it, we basically have to pay this $8 million every 70 years. Okay. And so basically the way that you can think of this is that the city basically has to pay to almost kind of replace the pipe every 70 years. Okay. And so we can just draw the cash flow diagram for this really quickly. Okay. And so at year 0, year 70, and year 140, okay, basically the cash flow diagram just looks like this. And so it's an $8 million thing that we have to pay every 70 years. Okay. And so the company, or so the city, they don't want to raise $8 million, every 70 years. So they say, let's pay for the pipe now, and let's set aside some money that we can put into some investments, so that every 70 years we'll have the money ready to buy the pipe. Okay. And so the question is, what is the capitalized cost that we're going to do, that the city needs to put aside in order to maintain this pipe? Okay. And so what we're gonna have to do is basically factor in the initial cost, and then also factor in all the replacement costs. And we're gonna use the formula that we did on the previous page as well. Okay. All right, any questions on this example? Okay. So let's go about solving this, okay? And so if we go back to our capitalized cost formula, we know that we need an A value, right? But right now we don't have an A, so we have something weird where we basically are just paying to replace the pipe every 70 years. Okay, and so well, we first have our $8 million in initial money, but that $8 million that we're going to pay out in the future, that's basically a future sum. Okay, so the $8 million. Let's just consider just the first replacement for now. Okay. And so because it's a future sum, we can't just directly apply into this formula. So the first thing we need to do is we need to convert that future sum into a uniform series. Okay. And so this is most easily done with the compound interest tables, right? And so we have 8 million, and we need to convert an F into an A. So that's going to be an A over F factor. Or I think I forgot to give the interest rate. And so let's assume that we have an interest rate of 7%. Okay. Right. And then 70 years. And then what we get is $4,960. Okay. Okay. So first of all, let's kind of pause and just see like how crazy interest rates are, right? And so, you know, if you make an investment of $4,960 at 7%, and you wait 70 years, so let's say that you want to give a present to your grandkids, you know, that initial investment of almost 5,000 is going to be worth $8 million. So you can see interest rates are crazy, right? Okay, and so in order to so now that we have our uniform series, we can just take this guy and plug it right into our capitalized cost formula right here. Okay, so our capitalized cost is simply just going to be our 4,960 divided by 0.07. Okay, and this is going to be $71,000. Okay. Right. And so our total cost, because remember we had to pay $8 million up front in order just to build a pipeline to begin with, is going to be $8 million plus 71,000. Okay, so our total cost is going to be $8 million, $8,071,000. Right. And so basically what this means is that in addition to that $8 million, if the city sets aside an additional $71,000 and just sticks it in a bank account with 7% interest, it'll automatically generate all the money that it needs to pay for the replacements every 70 years. So as long as they take that 71,000 and just don't touch it and just let it accumulate interest, then they'll have all the money they need for all the repairs for forever. Okay. All right. Any questions on this?
Wait, is the $4,960, is that per year?
That's per year. Yes. Yeah. And so basically what we said is that if we're gonna replace it at $8 million in 70 years, that's the same thing as saying, you know, we put like $4,960 each year towards maintenance. So they're basically equivalent in the same thing.
Professor?
Yeah. Mm-hmm.
Do local governments use like tax funding in the stock market at all to like raise their initial, not cost, but just to raise their money, I guess?
Yeah, that's a great question. I'm sure there is some, because especially in America, where, you know, a lot of everything is driven by the stock market. So I'm sure they do, but I'm sure there's a lot of restrictions on what they can use it for, and, you know, the gains that they can do it for. But I'm not too big an expert on that stuff to really comment too much. But I'm pretty sure that they would.
Okay.
That sounds like fraud. It could be. Yeah, that's why there's supposed to be rules for that stuff. Yeah, maybe through employee pension funds. Yeah, that's because a lot of times your retirement funds. That's the reason your retirement funds gain money over time, is because that money is being invested in, like, companies and all that stuff too. So it's very complicated. Yeah, we need to bring James back in order to kind of explain that stuff. I think probably he'd be better than I would.
Professor, can you explain again how we get the total cost at the end?
Yeah, so the total cost is basically our capitalized cost, which is what we got right here for the 71,000, plus our initial cost. Remember, at year 0, we have to actually build the pipe to begin with, which is $8 million. And so we do 8 million plus the 71,000, and that's we get $8,071,000.
So it's 4,160 per year, but what is the $71,000 for again?
The 71,000 is how much we have to put away at the beginning. Because remember, the way you can think of it as the way that we're going to raise that $5,000 each year, or the way that we're going to raise that 4,960 is by taking 71,000, stashing it in a bank account, and then just withdrawing the interest every year. And so basically what that means is that 7% of that 71,000 is going to give us this 4,960. And that's basically just what we're going to withdraw every year. So that 71,000, we're just going to leave it alone and then just collect on the interest every year, basically.
Oh, okay, thanks.
Yeah. Yeah, if you, yeah, the reason I did 2 kind of examples for this is that it is kind of a weird concept, but once you kind of talk your way through it and kind of work your way through it a couple times, it starts to make a little bit more sense. Yeah. Okay, so there's one more thing I want to go over. And so there's one section that I'm skipping in the notes, but it's not that big a deal. So, and you're kind of already doing it for the homework, and that's performing present worth analysis for more than one option. So all you have to do for that is just, you have 3, 4 options to just compute present worths for all of them and see which one's the best, and then just pick that one. So there's really nothing to it. So I'm just going to skip that one. And then I'm going to go to the next section on complications. Okay. Right. So up until this point, we've used present worth on a wide variety of situations. But it's not a perfect method. So there's some cases where present worth is going to give you misleading answers. Okay. Okay. And so I think probably this is best illustrated with an example, which is kind of an interesting situation. So this is like an actual example, not a theoretical example. Okay. And so let's say that you work for a company which mines precious jewels from the earth. Okay. And so there's a piece of land that your company wants to buy, and then this piece of land is going to cost $61,000, or $610,000. Sorry. Okay. And so, after you buy this initial piece of land for $61,000, the company expects to make $200,000 per year on this land for 10 years. Okay? And so we're going to have a yearly revenue of $200,000 per year. Okay. And this is going to last for 10 years. Okay, and so after your company's kind of done stripping, all the coal from this land, government regulations require that you kind of clean up all the stuff there. Okay, and so this is kind of a unique case because usually we have a salvage value at the end where we sell, our in this case our land for a certain amount. In this case, we're going to have a net negative at the end because we have to do a lot of cleanup operations, and so we have a salvage cost of $1.5 million. Okay. And so what I want you to do for this problem is to find the present worth of this investment to see if it's worth it. But I want you to do it at 2 different interest rates. So let's find the present worth at, we'll say that I1 will be 10%. Okay. And we'll compute a second present worth, and we'll say that the second present worth is 3%. Okay. Right. So this is kind of the first problem that we're doing with two different interest rates, because usually I just give you one, right? But ideally, what you want is that no matter what the interest rate is, you should still get the same answer. So basically, in this problem, what we're going to see is that if the net present worth is a positive number, that means we're going to end up making money from this. Then this investment is worth taking, right? But if it's a net negative number, then we're going to lose money on this investment, and this is not something that we want. Okay. And so ideally, what you would want is that no matter what interest rate that you choose, you're still going to end up a net positive, because that generally makes the most sense. But let's actually run through the calculations and see if that's true or not. Okay. So any questions on the problem setup? Okay, so let's do the present worth analysis for interest rate 1. Okay, so we have PW1, right? And so first, let's do the initial cost. And so our initial cost here is $610,000. Okay. And since that's already an initial cost in the present day, we don't have to convert that. Okay. Next, we're going to add our yearly revenue. So our yearly revenue is $200,000. Okay. And since this is a yearly revenue, it's a uniform series. And so in order to convert it to a present value, we have to multiply by P over A, 10%, and then 10 years. Okay. And then from that, we have to subtract our $1.5 million. Because that's our salvage cost, and that's going to happen at the end, basically, once we're all done, so in year 10. And so this is going to be P over F, because this 1.5 million is a single sum, right? P over F, 10%, and then 10 years. Okay? And then what we get from the present worth of 10 is that $40,750. Okay? Positive. Okay. And so since this is a positive number, then we're basically, by investing in this piece of land, our company is going to make the equivalent of $40,000 and $40,750 today. Okay. So that seems like a good investment. Not the best investment, because you would hope that something that you're spending $610,000 on, you'd make more money than this. But at least it's a positive. So it means that we invest in this land, we're going to make some money off it. Okay. And so let's repeat this calculation with the interest rate of 3%. Okay. Before I switch the page, does anyone need more time writing this down?
Shouldn't salvage be positive?
Yeah, so usually salvage value is positive, but in this case, our salvage value is negative because we have a salvage cost right here, right? Because we can sell this land afterwards, but because of government regulations in this case, they say that after you're done coal mining here, you have to clean up all the land. So in that case, it's going to be a net negative of $1.5 billion. So definitely, that's definitely the unique part of this problem, and we'll get back to it after we do the second part of the problem. Okay, and so let's do the present worth with 3%. So it's going to be all the same numbers, except that instead of 10%, it's going to be 3. Okay. And so let's just write it all in. Okay, so there's our yearly revenue, and then we're going to subtract our salvage cost. Okay, and then you look up those numbers in the tables, or you use the formulas, and then what you get is a net negative $20,150. And so we have a negative number here, right? And so for a 10% interest, we have, we say that the investment's good, but for a 3% interest, this investment is bad. So, which one is it, right? And so in these cases where the answer or the result of your analysis depends on the interest rate, okay? Okay. And when I say result, what I mean is not the actual numbers, because of course the actual numbers are going to change depending on what the interest rate is. But if that affects your decision on whether you should go with one option or the other one, or if you should say that this is a good investment or not, and so maybe the better word for this is decision. And so when the decision that you make from your present worth analysis depends on the interest rate, then present worth will give you basically unreliable results. Okay. And so just as Arturo pointed out earlier, is that the really unique part of this problem is that we have a salvage cost instead of a salvage value. Okay. Okay. So salvage costs are actually very weird and kind of unique. And in those cases, you end up with this kind of weird thing where depending on what your interest rate is, your present worth will either be positive or negative. And so these cases where you have something that's pretty non-standard and kind of pretty weird, then present worth might not be the best option for this. And so we're gonna go over different ways of analysis. So present worth is kind of just the first economic analysis tool, but over the next couple of weeks, we're gonna learn different analysis tools. So the next one that we're gonna do is annual cash flow analysis, which is very similar to present worth. Instead of calculating for P, we're calculating for A. And then after that, we're going to do rate of return analysis. So, in cases like this where, your decision is very heavily dependent on the interest rate, you might want to look into other economic analysis methods to make your decision, because present worth is not going to be the best. And so, if present worth gives you unreliable results sometimes, then, the question is like, why would you use it? And so people really like present worth analysis because it gives a very tangible thing to grasp. Because the way present worth works is that it gives you all the cash flows and everything summed up into just one number that you can look at right now. So like in this particular case, so if you had a 3% interest rate, you can say that if you invest into this coal mine and then do all the stuff, that's the exact same thing as someone like mugging you and stealing $20,000 from your wallet. So that's a very tangible thing that people can really grasp onto, right in the present. And so present worth is popular in that it's very easy to kind of interpret for a lot of people, but you have to be careful using it in some cases where it gives you unreliable results. Okay. All right. Are there any last questions on present worth analysis?
Professor, how did you decide when you're doing the calculations if you were gonna have use the PA from the table or the PF? How you decided that? Right.
So and so that depends on what kind of cash flow you're converting to what, right? And so in this particular case, for this 200,000, I used a PA because we know that this $200,000 right here, this is a cash flow that happens every year. So this is a uniform series. And so a uniform series is a type A. And so we want to convert that A into a P. And so the way that you use the table is that the thing that you're converting from should be in the denominator. So in this case, we're converting from an A. And then the thing that you're converting to should be the P, or it should be in the numerator. So in this case, we want to compute P given A. And so we want P over A. Right? And so for this particular case, you know, we're given 1.5 million. That 1.5 million is just a cash flow that happens once at the end of 10 years. And so that's a future sum because that's a one-time thing that happens in the future. And so in this case, we want to convert from an F to a P, where P is the present time value. Yeah, so it depends on what you're converting from and what you're converting to.
Thank you.
Mm-hmm. All right, so we're it's 2:15, so we're out of time today. So thank you everyone for tuning in. Hope you guys enjoyed the guest lecture from James on Tuesday. And then this is the end of present worth. So I think you should have everything that you need to do the homeworks. And then next week, we're going to start our next unit, our next chapter on annual cash flow analysis, right? And so I don't have the minute papers up yet, but if you wait 5 minutes, I'll have it up. And so if you can do the minute papers for the week, that would help me a lot too. So hope everyone has a good weekend, and I'll see you guys on Tuesday.
Professor?
Oh.
Go ahead, bro.
Mm-hmm.
I missed the first like 4 minutes of class. Do you mind going back to like the first slide so I can catch whatever I missed?
Yeah, definitely.
What do you mean by unreliable results? Do you mean like we can't choose between present worth number 1 or present worth number 3?
Right. Yeah, that's what I mean. So if you what unreliable results means is that basically if you do present worth analysis, like in this case on product A, product B, and then product A comes out on top, but if you change the interest rate, product B comes out on top. That means that it's unreliable. Yeah. So it's unreliable if it affects the decision that you're going to make, the engineering decision.
All right, I'm good, Professor. I didn't miss anything.
Okay, great.
Thank you.
Mm-hmm.
Professor?
Yep, what's up?
Yeah, I was wondering if you could explain the early salvage value.
Yeah, sure.
From the example.
Sure. Yeah, so early salvage value, so that occurs when you're comparing two different options and the product lives don't really match up that well. So like in this particular case, we have a product which lasts 7 years and a product which lasts 13 years. So normally when you have different product lives, you try to find the least common multiple of them, and then you do the analysis based on the least common multiple. But in this case, there's no least common multiple between 13 and 7, and so the smallest one is just their product, 13 times 7, which is 91 years. And so most cases, unless it's a public works project, you're not going to be using a machine for 91 years. And so in these cases, you do the analysis based on how long that you plan to use the machine. And so what that means basically is that you're not going to use the machines for the entire life it's designed for. And so for this example, we have one option which is designed to be used for 7 years, and then another option which is designed to be used for 13 years. But let's say that you work for a company and you only plan to use it for 10 years. And so what you're going to do is you're going to sell the machine earlier than what it's intended to, and so you're going to get back more money than if you sold it at end of life. And so that's what these values are right here, which is like for product A's case, if you sold it after using it only for 3 years, you would get $20,000 instead of $10,000. And then for option B, if you sold it after 10 years instead of 13, you would get $15,000. So all of these numbers I would have to give you because there's no formula for this because it really depends on what machine or what device it is and what you need for that. But it's just I just want you guys to be able to use this in an economic analysis sense.
So why wasn't it under like year 3, the $20,000?
Say it again.
Why wasn't it under 3 years, like year 3?
Oh, because basically we for this particular problem we wanted to use it for 10 years, and so I did it for 3 years right here because 7 plus 3 is 10. And so
Okay.
we use the first machine for 7 years, and we use it all the way up until it's done. And then the second machine that we buy, which is we buy a replacement, we're only going to use it for 3 because we're only going to use it up to year 10, basically.
Oh, okay.
Mm-hmm.
Got it. Thank you.
Yeah. Mm-hmm.
Professor, I'm still a little bit confused about the present worth.
Yeah.
So the only way it would be reliable is if the interest rate is the same for both?
And so it would be reliable if the decision that we make is the same for both. So for the last example right here, way back. And so for the last example here, we're basically determining, the decision that we want to make is, do we want to invest in this land or not? And so it would be reliable where, like, if we did this analysis with 10% and we got a net positive number. So a net positive basically means that, this is a good investment and we're going to make some money. And so if we did the same analysis at 3%, and we get also a net positive number as well, say that this was like a positive 20,000 instead of negative, then our decision is the same depending, no matter what the interest rate is, then those results are reliable. But in this case, we got a positive number for one interest rate and a negative number for another one. And so we can't say that the results are reliable.
But doesn't that mean that we lose money on one and the other one is beneficial?
Yes, that's exactly it. So because based on the interest rate, for one interest rate we make money and for the other interest rate we lose money, then that's then you don't really know what it is or not. So in these particular cases, we need to use a different analysis method, which is what we're going to cover over the next couple of weeks. So present worth is just one method that we can do for economic analysis, but we're going to cover different ones in the next few weeks.
Okay, so technically this is not wrong. This method is not wrong.
Yeah, it's not wrong. It's just when you get kind of weird results like this, then you want to back it up with a different method to see which is the right way to go about it.
Okay.
Yeah.
Thank you.
Yep. Mm-hmm. All right. You guys have any final questions? Okay, so I'm going to end the call. So I'll see you guys on Tuesday.